In this video, we discuss about the paper Squeezed Spin States. In this paper, authors have established the definition of squeezed spin states. They proposed two mechanisms to produce these squeezed spin states. They are termed as one-axis twisting and two-axis counter twisting. The authors have also discussed about implementation of spin squeezing in interferometer. This paper starts with the consideration of spin system denoted by spin operators, which is a vector operator. The components which are along three orthogonal directions satisfy commutation relation. So therefore, they are associated with uncertainty relation. To define squeezed spin states, first we need to define coherent spin state. A coherent spin state denoted by theta phi direction ket theta phi is an eigenstate of the spin operator s of theta comma phi with the highest eigenvalue s. This state satisfies the minimum uncertainty relation with uncertainty equal to s by 2 along any two orthogonal directions perpendicular to the direction theta comma phi. To establish the definition of spin squeezing, first we need to consider a spin S system as made up of 2s elementary spin half systems. A coherent state ket theta comma phi is the collection of 2s spin half systems all pointing in the same theta comma phi direction. So there exists no correlation among these spin half systems. Therefore, the variance perpendicular to theta comma phi direction is just the sum of variances of all spin half system in theta comma phi direction. If the appropriate correlations are established, then one can reduce this variance in one direction. So now one can define squeezed spin state as the state for which the variance of spin operator perpendicular to this mean spin direction theta comma phi is less than the value s by 2 which is obtained from coherent spin states. So we need to find a state which has the variance perpendicular to mean spin direction. The variance should be less than the value obtained from coherent spin state. Then we call this state as squeezed spin state. This is the definition. Now in this paper there are two mechanisms have established to produce these spin squeeze states. So one of the methods is one-axis twisting generated by a class of unitary operators. So that is given here, and here the one has here in this example the lowest order nonlinear interaction is considered. So the initial state is the coherent spin states. The operators evolve under this unitary action and then rotate the coordinate system around x-axis. We have considered here a function of sz. So if we rotate around x-axis, then we get the corresponding expectation values. Only the direction along x will survive, all other expectation values will be 0, but we have variances along x, y and z direction. That is given here in equation 2 and 3. Right? So now one has to search for minimum variance in the yz plane. With the suitable choice of parameters, one can reach up to the value as given here, half of s by 3 to the power 1 by 3 asymptotically. This is the minimum variance one can achieve. So we can see this from this figure that where one axis twisting gives the value less than the variance value compared to the coherent spin states. We can reduce even more using two axis counter twisting. It can be obtained by twisting a spin operator about two axis simultaneously. So we can write the Hamiltonian for this, and for this case the variance is less than value half for small s, and asymptotically it approaches to the value half for larger values of s. So we can see from the figure that this is very much less than what we have obtained results from one axis twisting. So the next question arises is how to implement these one axis and two axis twistings in experiments. So one of them application is in interferometer. So consider n number of particles, quantum particles, partitioned by a 50% beam splitter, and it gives two outputs A and B. In this output, each particle is in a superposition state in which either it exists in A, not in B, or it exists in B, not in A. So this is kind of superposition state. Input is the n number of spin half particles, which this constitutes a coherent spin n by 2 system, and it passes through 50% beam splitter, and these equally partitioned as A and B. So the uncertainty for particle number difference and phase difference are given in equation 8 and 9. So now how to bring squeezing in this, how can we twist this spin n by 2 system? This can be done by bringing the population difference among between the outputs A and B. The interaction Hamiltonian is given here, which performs one axis twisting. The two axis twisting can be achieved by using four-wave mixing as given here in the reference 7. So this is how one can establish one axis twisting and two axis twisting in this interferometer. So what is the advantage of squeezing in interferometer? So we can see from the uncertainty relation we have delta and delta phi is greater than 1, which is followed from the uncertainty relationship. A phase difference smaller than delta phi is not detectable by interferometric measurement. So spin squeezing can reduce this delta phi without violating the uncertainty relationship. Therefore, it improves the interferometric sensitivity. This is the application of spin squeezing. These are all the important results of this paper. Thank you.